Briefing progress.
We'll just leave that there and that will pick me up. You can hear me okay? So thank you for that really nice introduction. I do in fact know Don Cantfield very well. We overlapped in graduate school, and I'm going to talk I'm going to talk about Don and his work quite a bit tonight. Okay, we have the mystery cursor problem again.
I found the cursor before. Perhaps I can do it again.
Well, I have the cursor, but I don't have that.
Yeah. So, pop over here. Got it.
Thank you. Yes, thank you. It's really a great pleasure to be here. I've known about this meeting for many, many years, and I should give you a sort of a qualifier. This is the last week of our classes. I'm going to Morocco on Wednesday, and almost everything I do deals with iron. And so I've had to figure out how to distill this down in amongst all of those things in a way that might provide a little bit of context of the kinds of games that people play with iron. And so I'm going to focus on deep time, but there's modern system calibrations in all the things that we do. So like Don and many other people, I spend, at least, and my students spend at least half the time working in the modern ocean to develop proxies and an understanding of how to validate and calibrate these things to increase our knowledge and our confidence in applying these things in deep time. And the truth is that they're incredibly powerful for almost everything that people are doing in terms of reconstructing ancient redox. But they are risky. We're arguing for primary signals that have been preserved over hundreds of millions and billions of years, and rocks that have seen great offenses that you're all well familiar with, from tectonic to metamorphic and on and on. And so primary mineralogies are seldom preserved. But the hope is that signals can be seen, primary signals can be seen through those overprints. And at the end of the day, what I got from talking to folks here is that perhaps what I should do is talk to you about the things that we're doing, and maybe you'll come up with ways to help us do what we do better, including the idea of using magnetic approaches to try and gain increasing confidence in the preservation of primary signals. So we're here in Minnesota, and you would think that I would, cursor is missing now again. There it is. You would think I would give a long talk on iron formations, and in fact, that's not really what I do. It's hard to work in the Archean and Proterozoic and not think about iron formations, but I think more broadly, and I'm going to give away a punchline right now that is the theme of much of the talk. We tend to think of iron formations as mirroring a time in Earth history when the ocean was rich in iron, and that's very much true. But what our results show, and the work of a lot of other people, is that the deep ocean was, if not rich, at least dominated by dissolved iron rather than sulfide and oxygen for almost all of Earth history, extending well into the Paleozoic. And so that begs questions of why are iron formations where they are, and how do we know that, and what does that allow us to do in terms of trace elements that are associated with these environments. And so I'm really going to give you just a series of sort of vignettes of the sorts of things that we do. And at the end of the day, the hope is that you'll see avenues into approaches that might enhance some of the quality of this. I also am going to try and give you some historical context in a way that maybe Rob Raiswell, Don Cantfield, me, and Bob Berner, if we were still alive, could do. Like the evolution of these proxies, where they came from, how we use them, why we use them. And I think the value of that is that there are a lot of misconceptions about what they actually mean. I think people imagine there's a set of sequential extractions that we just throw fairly simple wet chemistry at and we're done with it. But in fact, they're grounded in a very, very deep mechanistic understanding that began with Bob Berner really in 1970, and then Don Cantfield as his graduate students, and then Don and I overlapped. And I worked in the Black Sea, which is a great place to work if you care about anoxic modern systems. That was my PhD. And so you'll have something I haven't done for a very, very long time. It was in a class some years ago, some perspective of the evolution of how we got to where we are in using these things. But before I do that, let's talk a little bit about iron formations. And again, these are areas of interest for all of you, there are certainly important frontiers of research that lie with the delineations of primary iron minerals for iron formations. And so they're typically viewed as iron 3 hydroxides or iron 2 carbonates or silicates. Although, as I'll say in a second, green rust has received increased attention recently. So probably you know what green rust is, but I'll talk a bit more about that in a second. And these precursor minerals, which are essentially never preserved in their primary forms, they might be the same mineral, but the textures would be different. There would be dramatic changes, including for sulfide minerals. These precursors ultimately resulted in the iron oxides, including magnetite, which is really abundant in iron formations, but not so abundant in the modern systems. Silicates, carbonates, and sulfides that, as it says here, dominate the deposits as they're preserved today. And so green rust is an area of interest from a number of groups. Ite Haleve has thought about it. It's a layered hydroxide. It's mixed valent, ferric and ferrous, and it has substituted within this layered structure varying amounts of carbonate and sulfate and chloride and hydroxyl with varying amounts of water also associated with it. And so green rust also has been argued by Simon Polton's group to have important controls on the availability of nutrients within marine systems, and in particular, the absorption of nickel onto green rust. And nickel is important, as you'll hear later, as an enzymatic cofactor for methanogenesis. So methane is very important in understanding the evolution of our climate, and the degree to which life can produce methane depends very much on the amount of nickel within the ocean. And that depends very much on how much is being scavenged by green rust and other oxides within these systems. So nickel is purposely included in some detail in this. Nick Tosca has really sort of resurrected interest in greenolite, which is an iron silicate, as a precursor. So what you're getting from this, I hope, is that we really don't know what the precursor minerals were. And that's a problem, right? Because if you don't know what you started with, it's hard to know the degree to which they're preserved, and specifically carrying primary signals along with them. There is an issue with greenolite, and this is where the holistic view of these oceans come into play. And I'll show you a figure in a second, but we generally think that pH was low during the Hadean and Archean and even extending into the Proterozoic, because remember, this is a common theme running through. The sun was significantly less bright early in our history, only 70% as bright at the beginning of Earth history, and it became progressively luminous through time, and it is now as well. And through the silicate weathering feedback, CO2 has responded. It's been decreasing progressively over time, but when the sun was less bright, it was very high, and it continued to be high through the Archean and Proterozoic. And essentially every pH model that I know of argues for pH is not like the ocean today, which is around 8, but more in the 6 to 7 range. So that immediately puts constraints on what kinds of minerals could form and how well they would preserve. And greenolite, as I've said, is a challenge. Ite wrote a nice paper where he looked at these things theoretically, and on the left you see the thermodynamic predictions across EH-pH space in a hypothetical early ocean, early seawater, and it's hard to know exactly what early seawater was, but we can take stabs. There are upper limits to how much iron can be because minerals start forming, upper limits of how much silica can be in the ocean because minerals start forming if you reach saturation. And pH is reasonable to predict because we know that CO2 was high. And so because of kinetic problems, remember at low temperatures, thermodynamics often doesn't control the system that we see. Because of those kinetic issues, the reality was probably something closer to this, but the pH was probably somewhere in this space. So again, it's really sort of hard to know what those primary minerals were. And so here is Ite's version of pH through time. And Josh Crittenden-Totten and others working, David Catling at University of Washington, a number of people have modeled pH primarily based on assumptions about CO2. And so here we are at 4 billion years ago when you see pH is not much above 6. So you hear a lot of talk about early alkaline oceans, but that's not so popular an idea anymore, particularly because of the high levels of CO2 that are inferred to maintain a liquid water containing surface Earth. And so as the sun gets brighter, the amount of CO2 correspondingly decreases through the silicate weathering feedback. As it gets hotter, the reaction of CO2 dissolved in water forming carbonic acid increases. And so as a modulator, a thermostat of sorts, the CO2 draws down as the sun gets brighter. And so the pH is correspondingly rising through time to the pH that we have today, around 8. Of course, that's decreasing because of the CO2 that we're putting into the atmosphere through fossil fuel burning, but it's still around 8. And so if we look at the temporal distribution, and I flipped that because one of the big problems in my community is that people can't agree which side to put the present. And so I think I know the right answer, but anyway, sometimes you have to adjust your eyes with a collection of plots because they're not the same, or you flip them like I did. And so we know that famously banded iron formations and granular iron formations are abundant in the latest part of the Archean and into the Paleoproterozoic. And so the early Paleoproterozoic and then a big resurgence of them, as you all know, in the later portion of the Paleoproterozoic. And that's really pretty much it. There's that last blast until we have some occurrences associated with the glacials in the Neoproterozoic. And then, of course, in the Phanerozoic, we have iron stones, which are fundamentally different. They're more like oolitic deposits. They're iron-rich as well. Then we use them for their proxy value, but it's a different beast relative to these. And so I've given you a punchline already, and I'm going to hopefully convince you that it's right, that we had iron-rich conditions in the ocean through much of Earth history, yet we don't have iron formations through Earth history. And so Isley and Abbott recognized this a long time ago, and many other people have run with this theme, including Andre Becker, my colleague, and Kurt Konhauser. We had a review paper that came out a few years ago. And so the basic idea is that when you get these pulses, there must be something else going on. And that includes the idea of increased rates of seafloor spreading or large igneous province activity, and then ocean chemistry as well. So for example, work that came out of here with Lee Kump, the argument was that when sulfate was low in the ocean, hydrothermal vents released more iron. And so you, by virtue of having low sulfate through the Archean, and I'll make a case for that later, and even extending into the Proterozoic, the vent fluids would have correspondingly been higher in iron than they would have been in subsequent slices of Earth history when sulfate began to grow. Remember, sulfate is tracking oxidative weathering of the continents. It's sulfides that are weathering in the presence of oxygen in the atmosphere. And so we can a priori assume that the early ocean had very, very low sulfate, and that was conducive certainly to having dissolved iron, because it's always this battle between iron sulfide precipitation, which is titrating out the iron. And so if there is a lot of sulfide production, you may end up with a euxinic ocean instead, like we have in the Black Sea, which is famous for being anoxic and hydrogen sulfide containing and having vanishingly small amounts of iron because of the sulfide. And so having small amounts of sulfate and therefore bacterial production of sulfide through all of the Archean and into the Proterozoic would have favored iron dominance relative to euxinia. And so here are some of the arguments for low sulfate. They basically have to do with the magnitudes of fractionation that we see in sulfur isotopes as related to bacterial sulfate reduction. And so we know that there are a number of different controls on the discrimination between sulfur 34 and sulfur 32 in particular, as bacteria reduce sulfate to sulfide. And one of the primary controls is the amount of sulfate within the system. When sulfate is very low, the fractionations are very small. And so that's really what you're seeing here. At very low, these are experimental results, and they can be extrapolated to the observed fractionations that we see in the Archean. So when sulfate is very, very low, we have essentially no fractionation. Sulfate reduction is a very complex, multi-enzymatic, multi-step process. And it has a reverse nature to it. Sulfate diffuses into the microbial system and back out. And that's how the isotopes are expressed within the sulfate pool of the ocean. But when sulfate gets very, very low, it's really a one-direction process, and you don't have a net fractionation. But these are very, very low levels where these fractionations are small. It's less than 1% of the modern ocean value. Sulfate in the ocean today is about 28 millimolar. It's the second most abundant anion in seawater, second only to chloride. And so this value of less than 200 micromolar, as I said, less than 1%, And it would have favored high iron because of the low sulfate and therefore sulfide that would be produced by bacterial sulfate reduction. So experimental validation of this, but more recently, Sean Crow, one of the many really terrific papers that have come out of his work in Lake Matano in Indonesia, what Sean argued based on fractionation observations in Lake Matano and comparing it to Archean sediments. So here's delta 34S. Most of the values are clustering near 0, which is the primordial value. That's the igneous sulfur value. And so when bacteria kick in, you tend to get a lot of light fractionations and you tend to get a broad range. So when things cluster in a narrow range near 0, there's probably not much sulfate in the system, or there isn't much life happening. Well, we know that these are bacterial pyrites. And so these values, as calibrated by looking at Matano, argue for extremely low sulfate, 2.5 micromolar versus 28 millimolar. So first big take-home message, sulfate was very low in the early ocean, and that allowed for these abundances of iron. And so again, here's a very simple depiction of sulfate reduction with organic matter as the electron donor and sulfate as the terminal electron acceptor. And the hydrogen sulfide is produced, and it's reacting with reactive iron minerals that we'll talk a lot about, and you get these precursor phases that are amorphous FeS and other minerals that you're familiar with. And then through processes that are not actually terribly well understood, either involving sulfur intermediates to get from FeS to FeS2, or there is also an H2S pathway that involves H2S in the FeS getting to FeS2. That's been made popular by Dave Ricard, who has really pushed that idea. But the bottom line is that when you have a lot of sulfate, you're producing sulfide and titrating iron out of the system. When you look at the Archean, we have argued for a whiff of oxygen about 2.5 billion years ago. And so it was a transient oxygenation event in the atmosphere. There wasn't very much oxygen. It didn't make mass-independent sulfur fractionation go away, but it was enough to oxidize pyrite on the continents and deliver some amount of sulfate. And so there is an example at 2.5 of at least locally, a time period where you had sulfitic waters. Euxinic waters is the term that we use. Euxinia comes from the ancient name for the Black Sea, Pontus Euxinus. It means specifically a lack of oxygen and hydrogen sulfide containing. And so we argued for a euxinic episode related to an oxygenation event. And that's a theme that will come up again, how dynamic the transitions from one state to another are. Very low Archean oxygen. And then as we cross through the great oxidation event, that there was a lot of rising and falling, very dynamic, until we got to the next level, and the same kind of dynamic behavior persisted. And so one of the big questions has always been, if these iron formations are forming from oxidation of iron within an iron-rich ocean, and the abundance at a given time relating in some way to higher iron fluxes into the ocean through tectonic processes or dramatic reductions in the amount of sulfate, a combination of things. And when we have this iron, how do we oxidize it? And so as you'll see in a second, as we get closer to the great oxidation event, we can invoke oxygen, particularly in the surface oceans, because we, giving away another punchline, we and many other people think that biological production of oxygen by photosynthesis began long before the great oxidation event, hundreds of millions of years. And so the great oxidation event is really that balance between the increasing production of oxygen by life and the decreasing sinks, like by iron 2, and methane and hydrogen within the system, until you reach a tipping point in a dynamic way, and then you irreversibly accumulate oxygen in the atmosphere. But absent that, there are other ways of doing this. And I spent a couple of summers at the Max Planck Institute in Bremen of marine microbiology. And that group was famous for discovering this process within modern lakes. It's photoferrotrophy. It's an anoxygenic photosynthetic pathway. It exists today. We don't really know about its lineage, as you'll see at the end of the talk, but it's conjectured that it has been important throughout much of Earth history. Although we don't have a lot of genomic information, we don't have distinctive isotopic signals. It's a bit of a guess how far back in time it goes. But Kurt Konhauser and others have really pushed this idea, in particular, Andreas Kapler and Diane Newman at Caltech. And so this basically requires that you have iron within the shallowest portions of the ocean, within the photic zone. So it's a phototrophic photosynthetic process. And certainly you can do that in the Archean because oxygen is vanishingly small. So you could have iron right up to the air-sea interface and have lots of this primary production. In fact, it may have been a major pathway of primary production in the early ocean. And so Kurt and others have even looked at this quantitatively to imagine if the extent of iron formation that we see could be explained by photoferrotrophy. One of the big problems, though, historically has been that if all of this iron oxidation is occurring through a biological process, why do iron formations have vanishingly small amounts of associated organic matter? They are just, it's almost completely absent. So you could argue that it's been burned through by the reduction of the iron oxides through a process called dissimilatory iron reduction. And that's part of the problem, or part of the answer. But they published a paper, Kurt and others published a paper a couple years ago where they looked at, through experimental work, what happens with these photoferrotrophs. And what they found is that the photoferrotroph cells actually expel iron oxyhydroxides when there's silica in the system. And so the Archean Ocean is also famously rich in silica. We didn't have biological uptake of it, and so the iron formations correspondingly have abundant associated cherts, and so there's a lot of dissolved silica. So the conditions were right for this process to occur. And the basic argument is that even though it's a microbial process and the oxides are forming an association with that microbial process, there's a separation between the organic matter of the bacteria and the oxide itself. And they even speculate further that that organic matter ends up somewhere else, where it may have fueled methanogenesis, which could have helped warm the Archean climate. And so this is the latest version of my oxygen curve. It's, yeah. And the colors were not my choice. The journal said that's what you have to do. That's not how it was submitted initially. And so we've stuck with it through the years. And what you'll see is that it, going back through the years, going back to 2014 for the first one, that it's gotten increasingly more complicated. But here is the great oxidation event. We have vanishingly small amounts of oxygen prior to that, mostly as constrained by mass-independent sulfur isotope fractionations. But there are increasingly arguments for at least pulses of oxygenation, and there's the whiff, and we can debate whether that's real or not. We think it is. But what people are starting to show now, which is really interesting, is that as you go into the great oxidation event in the early part of the Paleoproterozoic, that it seems that mass-independent sulfur fractionation comes and goes, and glacial deposits come and go. So there seems to be this kind of dynamic up and down, oscillatory nature of oxygenation, which you would expect as you go from an oxygen, essentially oxygen-free world to one that contains oxygen permanently for the rest of Earth history. And so it happened in fits and starts. And then we have the famous Loma-Gundi interval where oxygen may have been quite high, and there are debates about how high it was, et cetera. But there's a very strong positive carbon isotope excursion during this time, which many people attribute to organic carbon burial, and therefore corresponding release of oxygen. And then the relaxation into the mid-Proterozoic to some intermediate value is a topic of really great debate. We think, based on chromium isotopes and many other things that I'll share with you a bit later in the talk, that oxygen stayed quite low during the mid-Proterozoic. And then there's a neo-Proterozoic oxidation event where it rose probably at about 800 million years ago, the suggestions are. And then it probably relaxed again. And the best guesses are that oxygen stayed relatively low, at least in the ocean, perhaps until the Devonian. So as I said early on, there are arguments that are popular now that the ocean may have been mostly, at least the deep ocean, mostly anoxic and ferruginous to the Devonian. But what do we really know about the deep ocean, as it says there? What do we, in the post-GOE world, what do we know? And so Don Cantfield would have talked about this really seminal paper that he published in 1998, where he just really did a thought experiment. There were very little data in this paper. And he said, let's model the amount of oxygen in the deep ocean based on the amount of oxygen that's assumed for the surface ocean. So this is done based on assumptions about how much oxygen is in the atmosphere, right? So you can pick different values. And then we have to imagine how much oxygen is lost in the deep ocean through respiration. Organic matter is produced, oxygen is released through photosynthesis. That organic matter lives, it dies, it settles to the bottom, and the oxygen is consumed through respiration. And so unless oxygen was very high in the atmosphere, which most people don't think, or respiratory demand was very, very low, Don was left with the unavoidable conclusion that the deep ocean was probably anoxic. He went a step further and argued that because we're now past the great oxidation event, we're weathering sulfide minerals on the continents. Sulfate is starting to increase in the ocean, and there's evidence for that. And so we have a mostly anoxic deep ocean with increasing amounts of sulfate. A plus B equals euxinia, the bacterial sulfate reduction. And so this Canfield Ocean that many of you have heard of was an idea that was really posited in this 1998 paper, but not based on a lot of observational evidence that there may have been widespread anoxic sulfitic or euxinic conditions in the mid-Proterozoic ocean. But we don't really know, right? Or we didn't know at that time. And so we started to think about proxies, and this is where all of you come in. It's this idea of using iron mineral-based approaches to make inferences about what the deep ocean was like. And so in 1970, Bob Berner presented something called the degree of pyritization. And the degree of pyritization ties to this idea of sedimentary pyrite formation. And it very specifically asks us to look at the reactive iron component of that system. And basically DOP, as he defined it in 1970, is the amount of pyrite iron, which we can measure using a technique called chromium reduction. So it's a wet chemical technique that allows us to extract sulfur that is bound as pyrite and then calculate the iron associated with that just by using the stoichiometry. So it's pyrite iron that's extracted or calculated from extracted sulfur divided by pyrite iron plus some residual amount of reactive iron that isn't pyritized, that hasn't been converted to pyrite. And so you can start to think there might be some environmental relationship here. The degree to which reactive iron is pyritized might vary as a function of a system that's oxic or ferruginous, iron-rich, or sulfitic. The problem was when this was defined in 1970 is that Bob pushed using a 12 normal HCl extraction. And for any of you who do wet chemistry on iron minerals, you know that that's really aggressive, right? It'll get the oxides, it'll get the carbonates, it will actually get a lot of silicate iron. It'll get a lot of phases that are not very reactive on short time scales. And so it confused things for a while, and that's what I want to talk about a little bit right now. Be that as it may, despite the fact that there were really, it was based on a really aggressive extraction, Rob Raiswell would come every summer when I was in graduate school, and he was working closely with Bob. And he started looking at ancient shales and making this degree of pyritization measurement. And this was really sort of a seminal set of observations. So these are different shales, Jurassic shales from the UK, or excuse me, from Germany and UK, Upper Devonian, New Albany shale from the US, et cetera, Cretaceous shales from Colorado. Things by looking at the fossil evidence, you could make an argument that this facies was oxic. There are organisms, complex life, animals living within that were living within those sediments. And then there are other things that we could independently constrain as being anoxic, inhospitable, because they're laminated, there's no bioturbating fauna, there is no shelly fauna associated with that. And what Rob found, working with Bob, is that these things that were inhospitable had very high degrees of pyritization. And so the reactive iron phases were very strongly, almost completely in some cases, converted to pyrite. And you might expect that, right? Because if you think of a place like the Black Sea, there's a lot of sulfide. It's persistent, it's in the water column. The sediments are exposed to it when they're deposited because there's sulfide in the bottom waters, there's sulfide in the pore waters. And so what they really concluded in these papers is that the high degree of pyritization of these sorts of environments was associated with the high and persistent levels, as it says there, of exposure to hydrogen sulfide. But at the same time, and Don sort of entered the picture at this point, Rob and Don and Bob Berner were starting to think more about these different iron phases and what their reactivities would really be like with respect to hydrogen sulfide. Things like ferrihydrite and lepidocrosite, goethite, hematite, magnetite, reactive silicates, non-reactive silicates. And so Don, by looking at sediment columns and seeing the progressive conversion of mineral phases from their precursors to sulfidized phases, could come up with half-lives or rate constants, the rate at which different minerals would be converted. And so at the same time, Rob, working with Don and Bob, did a comparison of different extraction techniques and realized that the traditional DOP, as I've already mentioned to you, the hot boiling 12 normal HCl goes really deep into this pile, right? It extracts a lot of iron that is not particularly reactive. And so Don was really troubled by that, right? I mean, he said, listen, this persistent exposure to high concentrations of hydrogen sulfide, it must be something more than that to explain the high degrees of pyridization, the high extent of reactive iron sulfidation. And for Don, it really came together when he was looking at the foam site, which is this unassuming location just off the coast where Yale is located in Long Island Sound. And foam stands for Friends of Anoxic Mud. And so Bob created the location, and it was like a who's who list of people that came through, Marty Goldhaber and Raiswell and on and on and on. And so again, there's nothing particularly special about it, except that it's organic rich. And the pore fluids at foam contain 6 millimolar sulfide. Okay, I know I'm doing a lot of geochem here, but that's a lot. The Black Sea, the quintessential euxinic basin, is 400 micromolar. So this is 6 millimolar hydrogen sulfide within those pore fluids. And we know the sedimentation rates. And so what Don argued is that the sediments were being exposed to 6 millimolar sulfide for a century or more, for many decades, and yet the degree of pyridization is only 0.4. It couldn't be just this idea of having long, persistent exposure to hydrogen sulfide. And so the oxide to the dithionite to total, or what we call reactive iron, which is really dithionite to pyrite, its ratio to total iron was about the same. There was just nothing exceptional about this. And so Don began to think that, and I should say also that from my work in the Black Sea and other people's, the pyrite there forms in the water column. It's really fast. We call it syngenetic. It's forming mostly in the chemocline, that redox interface within the water column. So it doesn't take centuries and centuries of exposure. It's happening like that. Yet here at foam, despite a century of exposure to very high sulfide, the DOP is only an intermediate level. And so we published a paper, and this is really what put this iron speciation stuff into motion that many of you have heard. And it's controversial, but it's also extremely powerful if it's done carefully. And it provides the context for so many things that we do, including novel metal isotope approaches like molybdenum and thallium, trace metal mass balances that allow us to construct the entire redox landscape of the ocean in ways that I'll talk about. So it's hard to get away from using these iron speciation techniques. And so when Don and I and Rob Raiswell looked at Black Sea sediments, it was pretty clear that it wasn't just about this persistent exposure and you're just kind of burning through more and more of the reactive iron. What became clear is that there was more reactive iron. There was additional reactive iron that was easily pyritized that was brought into this system. And so the microlaminated deposits, that famous Unit 1 in the Black Sea, it's enriched in sulfide-associated reactive iron. And reactive iron, I should say, by definition, is that which will react with hydrogen sulfide on short time scales, diagenetic time scales of maybe decades, or even shorter. Sometimes it's nearly instantaneous reactivity. And so they're enriched by a factor of 2 to 3 compared to highly reactive concentrations in sediments from a variety of normal marine, which means oxic marine. Okay, it's not referring to salinity, it's referring to presence of oxygen within the system. So there was extra iron. And so for my work, Zilka Severman, who was my postdoc at that time, from our work, this is what Unit 1 looks like. It's amazing. These two cores were collected 200 kilometers apart, and they are virtually identical. The water column is so stably stratified that when the white layers, which are the coccolith E. huxleyi, form through blooms in the surface water, and the dark layers are mostly detrital material brought in by the Danube. When they come in, they travel along these isopyctal surfaces, these density surfaces, and get spread out through the whole basin uniformly, 200 kilometers apart. We couldn't believe it when we pulled these up. And what you see when you look at this material, which is here, it's called Unit 1, famously, it's enriched not only in reactive iron, as we concluded from that 96 paper, but it's enriched in general. So the total iron to aluminum ratio is high. Average continental crust is about 0.5, right? And so there's some variation of that, maybe by 0.1 either side, but 0.5 is sort of the universal value people use for the iron aluminum ratio of average continental crust, and therefore the detritus that's brought into marine systems from the weathering of continents. And so that's what that dashed line is. And when you go to the oxic shelf locations in the Black Sea, sure enough, they're about 0.5. But when you get to the deep basin, it's strongly enriched in reactive iron that manifests in a strong enrichment overall in iron. So thinking paleomagnetically, you have a lot of iron that's flowing within these systems, right? And so that gave rise to, fairly soon after this, in the late 90s, early 2000s, gave rise to this idea that many people buzz about now, the idea of a benthic iron shuttle. The idea that iron can be transported from an oxic shelf into the deeper basin where it can be scavenged by the hydrogen sulfide and pyrite forms. And that's what syngenetic pyrite is, that's forming in the water column. On the oxic shelf, the pyrite that's there is all diagenetic, is forming within the sediments because the water column has oxygen. But the truth is, in places like the Black Sea and many other places, there isn't very much organic matter in those oxic shelf sediments. And so the pore fluids are what we refer to as being suboxic. It means that they don't actually really get to appreciable amounts of hydrogen sulfide production. There's denitrification, and there's manganese reduction, and there's iron reduction. So those pore fluids are, and many of you will have seen these in modern systems you work on, and some of you are experts on this. These pore systems are rich in dissolved manganese and iron, and they're lacking nitrate because of the denitrification that in a delta G sense precedes all of those steps. And so what we concluded, and this has become now, I think, fairly widely accepted, is that iron that is released through this suboxic diagenesis, through dissimilatory iron reduction, because there's no sulfide to react with it, to contain it as pyrite, it actually diffuses out of the sediments and is transported in ways that people are still trying to resolve into the deep basin where it's scavenged and captured as pyrite, syngenetic pyrite. So that gives you the extra iron that you see in the iron aluminum ratio. It gives you the high reactive to total iron ratio that we talked about in 96. And here's like the smoking gun for this. There is actually an iron isotope expression of this. And so when dissimilatory iron reduction occurs, the light iron isotope is preferentially reduced and put into solution relative to the residual oxide. And so what we concluded was that I can remember sort of driving along thinking, we could do this. The more of this dissimilatory iron reduction that's occurring on the oxic shelf and then is transported into the deep basin, the greater the enrichment and the lighter the isotopes, because the iron within the system, just from detrital delivery, is being augmented more and more and more by the scavenged iron from the reduction on the shelf, which is isotopically light. And I'll be damned if we didn't see that. The higher the iron aluminum ratio, the lighter the bulk iron isotopes. Here is the oxic site where it's actually shifted heavy because you've lost the light iron isotopes to transport into the deeper basin. And here it becomes light because it's scavenged through that process. And so here is a really nice application of iron isotopes to do what we think is capturing the shuttle process. So the idea of a benthic shuttle is not specific to the Black Sea. There are many people, and Zilka in particular, and Jim McManus, and Will Barrelson, many people who look at shelfal settings have been arguing in places where particularly there's not very high organic carbon loading, that the suboxic pore fluids may deliver iron that can go into the deep ocean and have biological consequences, especially in areas where there's iron limitations for life. And so the idea of a benthic shuttle is important biologically, and it may be at the heart of trying to understand how this proxy works. And so much so that we can even start to imagine sort of variations on the theme. And this gets to some of these challenges of the method. It doesn't always work. That's fair enough. You have to think about the entire picture. You have to think mechanistically what's going on. And so what we have found is that if we look at the iron aluminum ratio, it actually becomes more and more, it becomes lower and lower and lower, I should say, as the bulk sedimentation rate or accumulation rate of the system becomes higher. So we have the Black Sea margin that has a sedimentation rate of about 1 centimeter per year. and then the deep basin, that's a couple orders of magnitude slower than that, and then intermediate sites. And so the basic idea is that this shuttle is delivering iron, and it's being enriched through the processes within the water column. But when the detrital flux is so high, it just basically swamps the system. And so the material looks detrital. The scavenging component becomes a minor fraction relative to the material that's coming in from the rivers. And then when it's slow, on the other hand, then you can get a really, really strong enrichment, as we see in the Black Sea. So another bit of information that we can get from this approach is sedimentation rate gradients, because we know that it's a balance between the scavenged iron and the detrital material that comes in with rivers. So Don and Rob and others started thinking very closely about how we can better characterize this reactive iron, doing something more than just using a boiling HCl extraction that will extract all sorts of different non-reactive or not readily reactive iron phases. And so they put together a really nice paper, Rob and Don, in 1998, where they looked at a variety of oxic settings. And they looked at total iron versus highly reactive iron, and they found this envelope of data. So these are data from many locations in the modern world that have oxygen in the bottom waters, shelfal environments, and found that there was this envelope. And this line right here defines the famous 0.38 threshold that people use to distinguish between oxic versus anoxic deposition that I'll show you in a second. And if you look at euxinic environments, what you see is that the highly reactive iron, in this case, it's oxide extracted dithionite iron, sodium dithionite extraction plus the pyrite iron. What you find is that these enrichments are greater than what you see in oxic environments. So here is this, again, the smoking gun, this enrichment of reactive iron. And so Don, working with Simon Polton, who was a PhD student of Rob's and then a postdoc of Don's, they developed a sequential extraction procedure to try and parse out, divide these different iron species in ways that many of you think about in terms of their relative reactivities. And you could sum things that have relatively short reactions with hydrogen sulfide and include that in the highly reactive pool. And you can have unreactive phases, and you can distinguish pyrite from oxide, from oxyhydroxide using this scheme. And here's just a short version of that. And I'm sure some of you use variations on this. The pyrite we can get from chromium reduction extraction. The ABS, the monosulfide phases, we get in bulk by using 6-normal HCl, cold, with stannous chloride. It's sort of an operationally defined procedure, but there's a vast literature on how people decided on that, and that's how we and many other people do it. Magnetite is done with ammonium oxalate, conventionally in this scheme. Carbonate bound is done with sodium acetate, dithionite, or the crystalline iron oxides, done as a step in sequence, but with sodium dithionite. And this really labile component of iron oxides, oxyhydroxide, is extracted with ascorbate. And so for ancient and modern systems, because we want to use similar approaches to be able to calibrate and validate, we march through these various steps. And so this is just one example of what it might look like going down core. This is a project that a student of mine just did in Saanich Inlet, which is it's an oscillatory redox system. It gets low oxygen and even sulfidic during certain times of the year. It's a fjord in southern British Columbia on Vancouver Island. And you can see these different pools. There's a lot of pyrite. There's a bit of ABS or acid volatile monosulfide, the monosulfide phases, and on and on and on. And so we and others do this for many, many, many different sedimentary systems. And when you do, through the calibration, what you find is that you can sort of break it out like this. Now, I would never encourage people to make a big deal about things near these boundaries. These boundaries have errors associated with them. But if you remember that envelope of data from the Raiswell and Canfield paper, where the oxic sediments at the upper level had a ratio of reactive to total of 0.38, that's where this comes from. So things that have a reactive to total ratio of less than that are generally ascribed to oxic conditions. Things that are ascribed that have higher values than that are generally ascribed linked to ferruginous conditions, unless there's a lot of associated pyrite. So the vertical axis is the degree to which the the reactive iron, and that's the sum of all those pools, other than the unreactive phase, how much of that has been converted to pyrite. So the first thing you would always do is run the reactive to total to see if it's anoxic, and then you would look at the pyrite to reactive to see if it's euxinic. And again, the boundaries of these things have shifted over time, but by and large, in the modern and ancient, this works. And so here are just some examples. These are data from the mid-Proterozoic, which we never expected actually to be a ferruginous ocean. As I'll say in a second, remember, people imagined that the transition from a BIF generating, an iron formation generating ocean to one that wasn't, was really about oxygenating the ocean or building up hydrogen sulfide in the ways that Don Canfield argued. But increasingly, what we were finding, and many other people, is that many of the shales, carefully selected not to be heavily metamorphosed, not to be heavily weathered, many of the shales plotted in the ferruginous. They were anoxic because they had the extra reactive iron, but they were not euxinic because the degrees of pyritization were quite low. These things on the boundary are hard to say, maybe oxic, but this ferruginous field was very well established. And so there was, surprisingly, especially within the context of the assertion of the Canfield Ocean, there were surprisingly few euxinic shales during the mid-Proterozoic. There were also gradients. And so the popular idea that came out of our work and work that Simon Polton was doing with Don Canfield and others is that most of the deep ocean, even in the Proterozoic, was ferruginous, and that sulfide in the Canfield Ocean sense was probably limited to productive margins, where there was a lot of organic delivery through primary production, and their sulfate reduction rates were high enough that the system could titrate out the iron and you could build up a wedge, if you will, of hydrogen sulfide, much like an oxygen minimum zone that we observe today. This kind of behavior has been observed in other places. This is from the Doshantou, the Ediacaran unit in South China. And here, similarly, we see a lot of ferruginous plotting data, some euxinic, again, gradients. So the idea of having a productive margin wedge of hydrogen sulfide with most of the deep oceans still sulfidic. I'm not going to talk about it, but we have a variety of techniques that suggest that oxygen was starting to accumulate in the surface ocean. During the Proterozoic, that's not a surprise. Eukaryotic life is developing. Animals evolved by about between the two glacials, between the Sturtian and Marinoan, between 600–700 million years ago. And so the oxygen was really mostly confined in the ocean to the surface layers. And so the thing that for us really drove all of this home is that we started to do a lot of trace element work. And so we have instruments where we can do bulk digests and look at the associated redox sensitive metals, focusing on a number of different things. Molybdenum is a favorite of ours, but we certainly look at uranium and a wide swath of in particular, first row transition elements. And what we found, again, by looking at modern systems, is that in permanently euxinic environments like the Black Sea and Cariaco, there's very strong molybdenum enrichment. In suboxic to oxic environments, molybdenum is low. The crustal value is about 2, so you get some enrichment, but it tends to separate quite nicely from those environments that are either intermittently euxinic or permanently euxinic. And so here is something that Eric Sperling just put together because he's been accumulating massive amounts of data. He compared highly reactive to total ratios and pyrite to highly reactive ratios to the metal enrichments that you see in the same shales. And it may just be dumb luck, but the really amazing thing is that if you look at uranium, that does not require sulfide to enrich. You can do it even under ferruginous conditions. If you look at the uranium, and this is many data, hundreds if not thousands of data, when you get to that threshold of about 0.4, 0.5, you start to see strong enrichments in uranium. And when the reactive to total ratio is lower, you don't. And similarly, in this massive data set, when you get to high degrees of pyritization of the reactive iron, high pyrite iron to reactive, and again, this is the sum total of that sequential extraction, when you get to values of about 0.7, 0.8, it's only then that you see molybdenum enrichments. So there is this independent, based on copious numbers of data, this independent constraint that the trace metals are saying the same thing that the iron speciation data are saying. And this is one of my favorite data sets. I have 2 different ones. One is from the early late Cambrian spice event, which is a carbon isotope excursion recognized throughout the world. And this is OAE2, which is a famous Cretaceous oceanic anoxic event. And the data that you're looking at right now are from a place called Demerara Rise, which some of you will be familiar with. Demerara Rise has the distinction of having been euxinic before, during, and after the oceanic anoxic event. And so if you're following me at all, and that's done based on the iron proxies, I could show those data, euxinic before, during, and after. Euxinia is required for enriching molybdenum. You convert molybdate to tetrathiomolybdate. It gets scavenged into sediments. Sulfide is very important for molybdenum, less so for uranium and many other metals, vanadium, so forth. And so you can imagine that at this local environment where there's sulfide in the bottom waters, like a Black Sea today, you can scavenge lots and lots and lots of molybdenum into the sediments. But as that oceanic anoxic event starts to become more widespread, molybdenum is depositing in many places throughout the global ocean. And so the concentration of molybdenum in the ocean would drop. So there's a decreasing inventory of the metal. And so that's exactly what you observe for molybdenum and other metals. As we go into, and this is based on the carbon isotope excursion, this is the OAE proper. As we go into it, and presumably anoxia, euxinia is becoming more widespread, the enrichments actually decrease, and then they increase again as we come out of it. And we see the same thing when we look at this SPICE event. This is another positive carbon isotope excursion. We've argued that it was at least locally, perhaps widespread euxinic, a widespread euxinic ocean. And there's the high DOP, the high reactive to total, the high total to aluminum ratio. All these things point to this place being persistently, this one location anyway, persistently anoxic and euxinic before, during, and after the event. And the event is defined by this positive carbon isotope excursion, lots of organic burial, which could support this condition of oxygen consumption and sulfide production. As you go into the event, you actually see decreasing metal abundances. So we got the idea that we might be able to do this on a global scale. What if we looked at euxinic shales through time? Now, there aren't a lot of data. That's because this is an old paper, and also because there actually aren't a lot of euxinic shales through the mid-Proterozoic. Most of them are ferruginous. And so we were pressed. We tried to find more data to add to this. But the basic idea is very much like what I just argued. What if you look at comparing apples to apples, euxinic shales through time, and you constrain them as being euxinic by looking at the iron proxy. So you need the iron to independently say it's a place that could enrich molybdenum. So if you do that, then the degree to which molybdenum or some other metal is enriched is presumably tracking something about global conditions. And so what we see very early in Earth history, and I'll show you a uranium plot that's much more impressive than this. Very early on, we probably had very low delivery of metal to the ocean because there was little oxygen in the atmosphere. These metals come from oxidation of continental surfaces. And then as we cross the GOE, we see an enrichment, but the enrichments stay quite low. And it's only here in the later portions of the Proterozoic, in the late Neoproterozoic, that we start to see values jumping towards present day values. And the uranium is even more like this. And so we have low delivery, a more oxic world. And so where you are enriching it, you're drawing from a big pool because generally the ocean is not sucking it down. And then an ocean that's still widely anoxic is pulling down uranium. And then around 800 million years ago, sometime in the late Neoproterozoic, everything jumps up again. So these enrichment patterns, as constrained using shales, as constrained using iron speciation, are telling us something about what the ocean redox was like. And so these are the steps that you observed in my oxygen curve. This is the great oxidation event, and this is essentially coincident with the Neoproterozoic oxidation event. And so we published a paper in PNAS a few years ago where we actually modeled the enrichment patterns and came up with an estimate for how much of the ocean was anoxic, ferruginous versus sulfidic. And we used chromium, which does not require euxinia, versus molybdenum, which does require euxinia. And so the Canfield Ocean now, based on these mass balance arguments, became 30 to 40% anoxic, potentially much more. And only 1 to 10% of the seafloor was probably euxinic. That's the sulfide condition that we have in the Black Sea. Now, 1 to 10% is a lot. Today, it's much less than that. But it was nothing like the Canfield Ocean that people envisioned not very many years ago, having hydrogen sulfide everywhere. And we can also estimate the concentrations of molybdenum in seawater at about 10 nanomolar. Today in the oxic world, it's about 100 nanomolar. This starts to be low enough where it could impact the ability to fix nitrogen enzymatically, because molybdenum is an important enzymatic cofactor in nitrogenase, in nitrogen fixation. So you can start to relate to biological processes, and that's really what people were doing. Max Sato, Ariel Ambar, us, many other people were starting to think about these prevailing conditions. And initially what people did is that, well, it was ferruginous. Everybody knows that because of the iron formations. And then it was euxinic because Don told us in 1998. And then it was oxic because we got out of that time and went into the Phanerozoic, and we know there was lots of oxygen around. And so then Mac did thermodynamic modeling to look at varying metal solubilities, and you can look through this redox transition of, for example, a world today that abounds in molybdenum, but early in our Earth and our history had very little molybdenum. A world that had lots of iron that today has very little iron. And so you can start to surmise perhaps that the high demand that present-day plankton have for iron might have been inherited from a time when there was a lot more iron. And similarly, we can ask questions like, why is molybdenum-based nitrogenase preferred over vanadium and iron, the alternative nitrogenases, when it was so low? And we just wrote a review paper where we're speculating on exactly those things. Another thing that you can do is, again, use the iron isotopes to try and understand a little bit about what the surface ocean was. So remember, dissimilatory iron reduction releases light iron that is captured through scavenging into the sediments of the deep basin. But when dissolved iron, iron 2, is precipitated, the oxides are heavy. And so when there isn't much iron in the ocean and there is plenty of oxygen, what ends up happening in these more recent times is that you're basically quantitatively oxidizing the iron that's available, right? And so it doesn't matter if there's a fractionation, you're consuming all of it. And so in ironstones in younger times and in the later portions of the Proterozoic, we see very, very, very little offset from the continental value, from the delivery. But when we go back in time, 1.6 billion years ago in the Proterozoic, 2.0 billion years ago, we see some really heavy iron in ironstones. We don't have iron formations at this time to look at, but we have these oolitic, piezolytic ironstones, and they provide a similar value in the way that people traditionally use iron formations. And so here we see very positive values, which suggests that there was iron in the water, that there was oxygen in the water, but it wasn't very much oxygen, so there was only partial oxidation, allowing you to express that fractionation that occurs during that process. So the simple measure in these ironstones of iron isotopes allows us to surmise, as it says there, strong evidence for a weakly oxygenated ocean atmosphere system during the Proterozoic. This is kind of $1 million prize, right? What happened to the ocean after the Great Oxidation Event? How high did oxygen rise? Did it rise and drop? If it dropped, how far did it drop? Were the levels low enough that they could have helped throttle eukaryotic development because they're appearing during this time in the Proterozoic? What role did the rise of oxygen play in triggering the evolution of animals? There is tremendous debate about all of that. And so I'll end with just some additional implications as we think about how iron is so central to all of this and the kinds of games that we can play. One thing, and those of you who know about the metamorphic and burial in general overprints on iron formations, you might cringe, but it's a fairly common thing for people to collect iron formations and to measure metals and phosphate, associated elements and compounds with the iron formation, with the idea that as the oxides and oxyhydroxides are forming, they're scavenging metals and nutrients from the water column, depositing them and retaining that relationship of nickel to iron or phosphorus to iron that is something close to how it began. And that's a really big question. So if you look at iron formations going back almost 4 billion years ago, one of the things that you see is that early on, they had very high nickel to iron ratios. And then as we get near the GOE, lots of stuff happens at the GOE, the Great Oxidation Event. As we get to that, we start to see decreasing nickel to iron ratios. What Kurt Konhauser and others argued in this paper, which they called an oceanic nickel depletion and methanogen famine before the Great Oxidation Event, the basic idea is that so many of these capture first-order tectonic relationships. And so the argument was that when the Earth was still hot and extrusive volcanics were dominated, or at least had abundant numbers of komatiitic extrusions, that there was a lot of associated nickel. And so the nickel is coming from these weathering of extrusive chromatic volcanics. And you can look at an iron formation that is in some quantitative or semi-quantitative way scavenging from that inventory of nickel. And it sort of fits, right? As the earth cools and chromatitites go away, the abundance of nickel in iron formations drop. And so perhaps as we get close to the GOE, nickel started to become a bit more limiting in terms of its enzymatic role for methanogenesis. That would have had really important climatic implications. It could have even played a role in the GOE. As we're not producing methane, we're losing methane as an oxygen sink, which may have played a role in triggering us towards the persistently oxic environment that followed. And so there are always experimental calibrations that are required with these things. You need a KD, you need a partition coefficient. And so Kurt recognized, as other people have, that the amount of silicon or silica within the system plays a role in terms of the absorption properties of nickel onto the iron oxides. And so they used a number of different values and came up with basically KD values that allowed them to estimate concentrations of nickel through time. Using these nickel to iron ratios that you observe on iron formations and iron stones. And so the argument is that at the GOE, it really drops off dramatically. And whether that triggered the GOEs or not is another question. But certainly, this played some role ecologically in the extent to which methane production had some climatic relevance. Another thing that a persistently iron ocean does for you is it exerts very strong controls on nutrient availability. And so Tom Laxo and Dan Schrag published a paper a few years ago where they said that slow oxidation of iron in solution in rivers would effectively scavenge phosphorus. So we know that phosphorus is very effectively scavenged onto iron oxides. That's a well-known relationship, and I'll show you another example of that in a second. So iron abounding within continental systems, but in particular within the ocean, and oxidizing in certain places, either through photoferrotrophy or through the abundance of oxygen now within the system, that oxidation scavenges phosphorus and may lead, as I'll say in a second, to the relatively low oxygen values associated with muted primary production during that time. Lou Derry argued for vivianite formation. So iron 2 that was in this system reacting with phosphate, forming the iron phosphate mineral vivianite. And that put a throttle on the availability of phosphorus through that time. And then Chris Reinhard and I and others published a paper where we basically invoked the iron trap that exists within the Black Sea. And so what you see is that as you come near the chemocline, which is this pink area right here, is that you're precipitating iron oxides at that zone. They're dropping down and so what are we? We're looking at silica here. But the critical thing is phosphorus. So phosphorus is being released through remineralization. It's being scavenged onto the iron oxide particulates. They're dropping down, redissolving, and then you're seeing the drop through pyrite formation. So there is kind of a trap that was quite common in the early ocean, where it was hard to get phosphorus from the deep ocean into the surface ocean because of the scavenging at that chemocline surface. And so this is the idea that Chris and Laxo and Schrag, that there may have been, because of this abundance of iron within that early system, may have been a phosphorus scarcity. And they used a Monte Carlo approach and said that O2 production, biological production, and O2 release from that was maybe 25% of today's. And Laxo and Schrag argued that it was maybe less than 1%. So this relationship between phosphorus and iron may have played a very big role in controlling the amount of primary production during this intermediate chapter of Earth history, where oxygen was higher than before and lower than it was after the Neoproterozoic oxidation event. Another thing that's come out of all of this is that Eric Sperling and many other people have been looking at these iron relationships, the reactive to total, the pyrite to reactive, looking at much younger intervals in Earth history. And what Eric found, I think quite surprisingly, using a very, very big data set and statistical analysis, is that the proportion of anoxic samples doesn't change that dramatically as you go through the Neoproterozoic oxidation event and extend into the Paleozoic. And so now, based on a number of different papers, including a molybdenum isotope paper published by Thijs Dahl, there is not universal acceptance, but a general idea that the deep ocean may not have ventilated until the Devonian. And so we may have had iron-rich, mostly anoxic conditions in the deep oceans extending well into the Paleozoic. And so what we're trying to do in these final slides is to imagine this landscape through time. And the green is ferruginous. So look how much of Earth history is ferruginous, extending all the way to the Devonian. Euxinia, not very abundant because of the low sulfate in the Archean. And then we start to see areas of the margins, those wedges that had Euxinia. And then oxic conditions starting to emerge in surface waters. And really the deep ocean ventilating not until the later portions of the Paleozoic. And then on top of that, you can map all of these different microbial processes. And so there's a very, very strong relationship between metabolisms related to methane and iron and sulfur and nitrogen. They relate strongly to each other because there are interrelationships amongst the products and the reactants that are involved in those processes. But more so, there's a very strong co-relationship to the overall redox evolution of the system. And so this photoferrotrophy that I keep talking about, it's really just inferred based on the idea that the proxies are telling us that there was high amount of dissolved iron in the ocean at that time. We don't have good genomic data for that. Iron oxidation, non-photosynthetic, is a widely held view, but it's not really constrained by phylogenetics. It's really only dissimilatory iron reduction that's pretty well known from genomic or phylogenetic approaches going back pretty deep into Earth history, well into the Archean. And again, the relationships with these fundamental steps in the ocean and atmosphere is really clear. And so we're starting to put together cycles of how these things might have looked. Early Archean with dissimilatory iron reduction, reduction via methanotrophy. Photoferrotrophy, we think, went very deep into Earth history and may have played a major role in generating iron formations. Reduction of iron via reaction with H2S. And so you can start to have varying levels of confidence based on what you observe. Another thing that, another example of what an iron-rich system can do, some of you will know that the anaerobic oxidation of methane through a tie consortial relationship to sulfate reduction was one of the really important discoveries of the past couple of decades. What our work has been showing, and a number of other people, is that there is also a pathway that's based on iron rather than sulfate, where you can anaerobically oxidize methane and reduce iron in the process. And so this is important on early Earth. It's potentially important even on places like Mars. And so this is a data set that shows an enrichment of reactive iron through rapid burial processes deep within the sediment. There's a sulfate methane transition, and we have high amounts of dissolved iron being released, almost certainly through this iron-based anaerobic oxidation of methane. An iron-rich ocean also has the capacity to generate abiotic N2O, which could have been an important greenhouse gas at this time. N2O is also posited to be an important biosignature in exoplanet exploration. And as Bruce alluded to at the beginning, something that we care quite a bit about. And so we can think about the iron conditions and the nitrogen within those systems and whether we have to worry about a biosignature false positive, or what, in other words, abiotic N2O, that we could confuse with biological production. And the short answer is, if you were to read this and read this paper by my colleague Eddie Sweeterman, is that false positive is very unlikely. And so if we see N2O in an atmosphere of an exoplanet, we might have pretty good confidence that there's a biological production of it. But on early Earth, because of the iron enrichment, we could have had greenhouse warming that came from that. And so there are lots of challenges that come with all of this. And in the recent years, there are papers that some of you will have seen that think about metamorphic overprints. How far can you take the assumption of a primary signal that's preserved over hundreds of millions and billions of years? And one of the minerals that people worry about a great deal, including us, is pyrrhotite, which can form at fairly low temperatures through metamorphism of pyrite, especially if there's organic matter within the sediments, temperatures on the order of 100 degrees or so. And so we do extract for pyrrhotite, and we make a correction for that. We do use 6 normal HCl with stannous chloride, and we've been debating whether to use hot or cold. Or some trade-offs. If you use 6 normal HCl with stannous chloride and it's hot, you can start to detect pyrite. And so we tend to do it cold. But we do make this correction, and most importantly, we try to avoid rocks that are metamorphosed. And so I don't really defend the concept of iron speciation. I defend our use of it. And it's very, very important to pick good samples. We wrote a review paper and others have as well. There's a decision tree in there. There are very specific protocols that need to be adopted before one starts making these relatively easy measurements. And so that's the Raiswell et al. Paper in particular, published in the American Journal of Science in 2018, that talks about all the caveats and the way we view them. And Sarah has brought together some really interesting challenges to all of this, and in particular is related to pyrrhotite formation, but other things as well, and bringing magnetic approaches to assess some of these minerals. And then there was a paper that came out quite recently with Fike and Halevi and others that it is a massive data compilation. And the truth is, in this paper, there are a lot of samples that we would not have used. There's uncertainty in the techniques that were used in the various studies. And so, we're being very careful not to throw the baby out with the bathwater, but there clearly are things that should not be analyzed this way. There are clearly bad data out there, but hopefully I've convinced you from the set of fairly careful experiments that we've done that it can work. And I think that's it. Thanks so much.
Okay, questions? Yeah.
I can repeat the question, and I can hear you, I'm sure.
Thank you, Bruce. I recognized with horror during your talk that I recall Don Cantfield's talk, so I must have been there 32 years ago. And it's not consistent with my view of my own age. So
How many years ago?
I'm horror struck.
It was 32 years ago.
Anyway,
yeah.
Yeah, so a lot of geochemistry that's hard for us to understand.
Right.
Many of us do read this work and try and grapple with it. And I think there's a lot of synergies that magnetic work can have alongside the type of work you guys do. I'd like to ask a kind of basic dumb question and then follow it up.
Sure.
You gave a view of the Archean Ocean as low sulfate,
Right.
Which I don't know a lot about the Archean Ocean, but it's interesting because magnetite doesn't survive sulfidic diagenesis, right? And so if the early ocean's dominantly ferruginous, that's good for us.
Yeah.
So my question is, how much pyritization do you expect in the Archean Ocean?
Well,
it's basically variable, is it variable? I mean, it's a bit of a naive question.
It's not a naive question because, there is plenty of pyrite in the Archean Ocean, right? This is something, so some of you will know that Hiroshi Emoto made a name for himself in many ways, but in particular by challenging all of this. Right? He thought that the early ocean was oxic. He thought there was plenty of sulfate, plenty of oxygen in the ocean. And he cites things like pyritic units like the Mount McRae, the 2.5 has plenty of pyrite. I would link that to a whiff of oxygen. We have 2.7 billion-year-old shales that have as much pyrite as modern organic rich facies do. So there clearly is sulfate, and there is, I think, almost certainly a kind of transience to that if you allow for this possibility of a very dynamic system. And just to elaborate a bit on that, it's a story worth knowing, I think, that traditionally people drove the spike for the beginnings of biological production of oxygen at 2.7 billion years ago. And it was based on a biomarker study, first authored by Jochen Brox, based on rocks collected in the Pilbara. And so Jochen felt soon after that published paper in 1999 that probably the cores were contaminated. They had been drilled by a mining company and sat for a long time. And so we got money from NASA and NSF to re-drill. We went to an overthickened place and there was a lot of chert. We didn't get down to the 2.7 level. That's how all the Mount McRae stuff happened. It was making lemonade out of lemons because we had that beautiful shale sequence. Then the Agaron Institute came along and they funded us to drill as deeply as we needed to. They had that money. And so we got to those shales and they were drilled and collected more scrupulously than any organic study probably has ever been done. There's a nice paper in PNAS by Kate French and others. and the biomarkers weren't there. They were originally argued to be evidence for cyanobacteria, propanes, and steranes argument for eukaryotes, which require oxygen. That went away. So we actually don't have any organic evidence for early oxygen production. Those rocks are just, it's like trying to do organic work on Mars. It's a big prize, right? If you can find it, it's the best thing, but it's also often the hardest thing. And that's true for the Archean because those rocks are just too buggered, right? And so that it's not where you would go to look for biomarkers. So there is increasingly a reliance on inorganic techniques. And so for example, Pongola in South Africa, we see molybdenum enrichments that are isotopically light, which is classically associated with scavenging onto manganese oxides. It's a beautiful signal that's preserved in those rocks from Pongola. And so the manganese oxides are gone now. The rocks are too metamorphosed, but the light molybdenum is there. And so there is an argument that's come out of MIT and other places for a manganese pathway equivalent to photoferrotrophy. But microbiologists have looked for that for decades and decades and not found it. And now there are suggestions that it might exist. The counter to that is that it's not just about oxidizing in a photic zone, you have to deliver it to the seafloor. And manganese oxides are incredibly soluble. And so we make the argument that you need to have oxygen all the way to the bottom. And this has given rise to these oxygen oases in the surface ocean. And so you're producing the oxides one way or another, but delivering them in an oxygen-containing environment. And that evidence goes back to 3 billion years ago. Clark Johnson argued for oxygenesis 3.2 based on iron-uranium relationships. The inorganic techniques are the best things we have right now. So there is oxygen production. There are these transient events. We've done experimental work with microelectrodes where we've shown that pyrite can oxidize. And the data just didn't exist. It was based mostly on acid mine drainage literature where people were measuring at high oxygen levels, pyrite oxidation. We took it down to very, very, very low levels and found that even you can sustain mass-independent sulfur fractionation, very low oxygen in the atmosphere, and still weather pyrite to a level that can deliver sulfate. And that's probably what the WIF was. So the basic argument is that there was sulfate, and like everything, it changed, right? The dynamic behavior is the theme here. And so there would have been times when there was more sulfate. But the most important thing is that there was a ton of dissolved iron. So any sulfide that was produced would have been scavenged as pyrite and would have been buried as pyrite. And in a system that had low sedimentation rates, you can actually model pretty pyrite-rich shales, even if there's not very much sulfate persistently within the ocean.
But pyrite locked up quickly.
Pyrite locked up quickly and was preserved. What we know today from the work of Bo Jorgensen and others is that 90+% of the sulfide that's produced in sediments is reoxidized. But that wouldn't have happened then. So it was a very efficient scavenging of any sulfide that was present. Under low sedimentation could give you pyritic shales. That's the argument. Okay. It's definitely there, for sure.
So, I mean, one of the interesting frontiers, I think, in our discipline is molecular clock evidence indicates that magnetotactic bacteria evolved first, or the genes for producing magnetotaxis within these bugs started around 3.2 to 3.4 billion years ago.
Right.
So if you want to go and hunt for them, you want to know that magnetite's going to be preservable.
And therefore not a lot of sulfide around.
If your sulfide is being locked up quickly by really highly available dissolved iron,
and you could do that.
Chance of preservation.
Right. And you know it better than I do that the half-life of magnetite is longer than an oxide or an oxide oxide. So the magnetite would go slower. Don did a great study in foam looking at the progressive pyritization. You know that, right? Yeah. So that's right. Yeah,
but the half-life still
pretty short.
Comparatively low. So
so
you kind of want to know that it's still survivable.
That's right.
Thanks very much.
Yeah.
So both within Archean oceans and within maybe not so modern, but more recent oceans. How does the long story short, how does salinity affect all these segments, particularly this the iron benthic shuttle that you're talking about earlier?
Yeah. So knowing what salinity has been through time is hard. Right? That's a tough one. You can get some estimates of things like that from inclusions in halite, but they don't go back that far. My former student, Stephanie Olson, who's at Purdue, has argued for a salinity effect that kept the Earth warm. And so basically the idea is that if salinity was higher, and there are some arguments for that, that sea ice formed more reluctantly. And therefore, if you don't have as much sea ice, then that changes surface albedo. And so you're reflecting less light. And so you get more warmth at a less bright sun than you would if you had a lot of sea ice. So there are suggestions that that salinity is varied for sure. There are also suggestions that the amount of nitrogen has changed in the atmosphere and the total pressure, but that's a different story. I think that, salinity has one effect in a place like the Black Sea, which I think, has really skewed a lot of our understanding, not always in the right directions. It's the perfect place to form euxinea. Like if you had a recipe that you were asked to write for a euxinic system, it would be the Black Sea, because it has a sill, so there's no deep water. So that deep water produced at high latitudes is cold. It's high salinity, hot, cold. It sinks and it brings oxygen down. That can't go through into the Black Sea. It's got the Med to deal with anyway. But the Bosporus sill is only 30 meters deep, so there's essentially no deep water that's coming in. The water that does come in comes over the Bosporus and sinks down because it's more saline than the water that's in the surface of the Black Sea. The Black Sea has a positive water balance. So the Danube is dumping a lot of water in. It means that it receives more fresh water than it loses water through evaporation. So it's actually exporting fresh water or intermediate salinity water. And so there's an estuarine circulation. And so here's the Bosporus, and the Med water is coming in, and it's saline about 37 part per thousand, and it's sinking down. And so the Danube water is coming in, and there's some entrainment. The surface water is only about 18 salinity. And so it rides across the surface while the Med water comes and sinks beneath that. And so the deep Black Sea has a salinity of about 22 because there's always some mixing that's going on, and the surface is 18. The point of all of that is that is an incredible stratification, right? And so the only other ingredient you need now is that you've got stratification where it's hard to vertically mix. You've got a sill, so it's hard to laterally mix. All you need to do now is have a productive surface ocean, and you get the nutrients from the Danube and other rivers. And so there's production that sinks once it's dead, and oxygen is consumed through respiration. As long as you're not replenishing it efficiently, it's really easy to get a well-stratified anoxic system like that. And so a lot of the proxies were developed there, including the iron shuttle and a lot of our understandings. And that the molybdenum isotope proxy was first developed there. A lot of these things were, and almost certainly very few ancient environments were like that. Almost certainly they were less stably stratified. I'll give you the example of the Cariaco Basin off of Venezuela, which is a pull-apart basin. It sits out on the shelf. It has a shallow sill around it, but it only has a thermal stratification. It doesn't have a salinity stratification. And so it actually mixes. Oxygen is injected at depth down to about 300 meters. And so it's very dynamic. And so it looks really different than the Black Sea. And molybdenum doesn't work there, actually. The molybdenum isotope system works beautifully in the Black Sea, but not in the Cariaco. The thallium isotope proxy doesn't work very well in the Black Sea because it's so restricted. Thallium is mostly controlled by the riverine input rather than the ocean input, but thallium works beautifully in the Cariaco. So, I mean, that's a long-winded way of saying that's not only salinity in an absolute sense, but how it parses in terms of stratifying marginal basins. Because remember, most of what we're looking at are places that were somewhere on a margin. The deep ocean is gone, right? And so there's always going to be this bias. And the way we get around that is by using paleogeography and trying to pick the best possible places we can that have the most likely chance of being passive margins rather than a Black Sea, and looking at a lot of different places more or less at the same time, and look for the first order patterns that we saw in some of those curves. Yeah.
Yeah, thanks for that sweeping overview, Tim. I have follows on this in some ways, and particularly to your decision tree statement.
Yeah.
I guess I want to sort of push a little bit on the sort of highly reactive iron to total iron as anoxia, and just sort of preface it by totally understand that this is being sort of operationally defined as being reactive to sulfide.
Right.
Mechanistically, that this works in a basin where you have the iron shuttle
Have the shuttle
mechanism,
working, yeah.
and where that is like empirically calibrated in devices today. But I guess this is sort of inspired by doing work in a couple of proterozoic successions recently, where there's published iron species in data that's like in that Eric Sperling compilation, and where the highest highly reactive iron total ratios are in the shallowest, most oxidized part of the system, particularly where you can see that there's pigmentary hematite and preserved hematite, which can give you like particularly high, highly reactive to total ratios, in part because you've had those oxidative processes that have actually liberated iron from iron silicates and turned them into something that is now going to be highly reactive.
How high are the ratios?
They can end up like this is in like good Cummings of Simon Bolton on the downside shale, where they argue this yeah, so the highest ones there, I think they're like 0.6, and those are in actually like the fluvial sediments that are like the fluvial floodplains, and then it's similar to the Chuar, the sort of highest, and there it's a very different type of basin, right? You're not out on the shelf where
you're not. They're funny kind of places.
But
not such and that you are both,
right? And so I guess that's part of like the decision tree sort of question, right? Because one of the things you see in both of those is that you have really high extractable iron in the thionite extraction, right? Because it's targeting there, particularly your pigmentary hematite, which if you sort of, that's like the most oxidized thing it could be, right? It's sort of fully oxidized dioxide and then a stable, which is super useful for us. Stable, and, forming from very hydrated precursors. You can often magnetically show that that's kind of early. So I'm not bringing up this example, right, to sort of push away all of it, but just it seems in that decision tree framework, there's sort of information that like you can bring about the mineralogy, which we can gain insight from magnetically, for example.
That's kind of the point.
Can play a role.
But what do the magnetics tell you? So I might argue in a place like the Nonsuch and the Chuar that they have very strong local watershed control, right?
Yeah.
So there could be, just extreme weathering relationships, and sure, you get that. You get laterites that deliver iron-rich material into a basin.
Yeah, I mean, I think what you get in those settings, right, is where it's oxide, you preserve the detrital hematite instead of it being reductively dissolved, which is in those systems when you go to greater depth with the same detrital, you see that stuff's gone.
Because there's very little organic material. So.
Well, there are in parts of this you are in the Nonsuch, actually, they get sort of organic. But you'll see where you get deeper water there, you'll actually you don't get all the way to sort of Euxinium, but you will get more pyrite, right? So you've sulfidized your hematite there. And then you'll see it's in the shallowest water parts of the system where you get pigmentary hematite, which is telling you about those sort of perihydrate precursors.
But what do the magnetics tell you? You preface this by saying that the magnetics might allow us to understand a novel source relationship.
Well, you can assign mineralogical to we did this work with Eric Sperling and Sarah Slosnick, where on each step of the sequential extraction, right? We took splits, did rock magnetic experiments, and then we're able to quantify what actually was coming on.
Right.
Like, for example, in the oxalate, we saw that, it was very small sort of like actual magnetite. But anyway, so the magnetics, you can get things about the timing. You can say that those detrital hematite particles record the field of the time they're positive. Same with the pigmentary. And then for the rock magnetic experiments, you could then diagnostically.
A couple of points. So one is that you're right that there is overlap, and we go into that a lot in the review paper, and I know other people do as well. And Sarah talks about that a lot as well. So you can get with one extraction step some portion of a fraction of another middle phase, and that happens. But I still am. Are you imagining that there's just a particularly iron-rich detritus that's coming into these basins? Is that the basic idea?
That's probably true, but I guess I'm more sort of saying that in places where whatever the detrital flux was like oxidized, and in this case, it's not saying that you're not in the deep ocean, right? But the application of the proxy in those settings has led it to say it's rigorous. But it's where you're like basically in a sort of, imagine you're on a sort of fluvial floodplain, and sure, you have some iron silicate precursors that end up being sort of leach down and give you hematite to the system. But if you went and measured that, it then has highly reactive total.
I think this is the critical question, and this is part of the problem, right? I mean, these steps are not that hard to do, right? People set them up in a lab, and all you need is an ICP to quantify the iron. And so there are a lot of data. And so I visit departments where they're, running short sequences, or running carbonates is a big issue. So there's been work done on that because carbonates are fundamentally iron minerals, and they have some very strange iron chemistry, for example. And so there has been, one of the decision tree steps is to avoid carbonates unless they have a high enough total iron content, which means they're dirty carbonates. And so, there are a lot of data that are not put into any kind of contextual context. And that's a problem, right? And so I would say that if you're dealing with a system that has a major ancient river system draining into it, if it is like the Nonsuch, an extremely strange sort of continental setting that's probably controlled mostly by local watersheds. The belt supergroup, right, where Sarah worked, right? It's heavily metamorphosed, and people have debated for years whether it even had a fully marine connection or any marine connection. So there are
that's the debate with the 2 RT.
Exactly, and so there are many, many times where you should either not use these or use these in different ways. There are also places like where we have the iron-based anaerobic oxidation of methane. That if you look at that a million or billion years from now, you would say it was greenhouse. It's not. It's off the coast of Argentina, but it also has an incredibly high sedimentation rate, extremely high reworking. The organic matter within it is really recalcitrant because it's been reworked really extensively. Basically, it went through a diagenetic sequence, then it was reworked and transported. So it's not supporting much iron reduction. It's not supporting much sulfate reduction. There's very little sulfate produced or sulfide produced. So that's the great question. Like, if that's a shale 100 million years from now, how do you infer any of that? And so you're never going to get away from paleogeography. You're never going to get away from the broad contextual.
I guess it's a little bit.
And I would also say that, and this gets lost, and sorry to interrupt you, but it gets lost a lot. The trace elements are huge, right? So if this is a ferruginous system, and it's in a semi-open marine environment, because you can get it so restricted like the Black Sea where the enrichments start to become muted. Your situation, for example, I would look for trace element enrichments, and they're probably not going to be there, right? Because it probably wasn't an anoxic water column. And so every time that we've coupled molybdenum, vanadium, and isotope approaches as well, but in particular just the elemental concentrations, every time we've coupled them, like those plots that I showed from Eric, at least in our first order sense, there's a very clear relationship where the iron proxies say it's probably this or that. The metals that are independently constrained in terms of their behavior go in tandem. So I would bring other proxies to bear on it. That's part of what I would do.
I think we're coming up to the dinner hour. And Tim's on to speak for 2 hours.
Yeah.
I think we can carry on these discussions.
Is that a quick question?
Just very quickly.
Yeah.
I'm curious about your Ventic shuttle.
Yeah.
And the degree of preservation of the iron monosulfides of the system.
Yeah, I know.
Particularly Briga, highly magnetic, and whether presence of iron monosulfides might bear on deposition.
So the Unit 1 sediments have essentially no iron monosulfide. The pyrite, and we know this from sediment traps as well, and we also know that there's a subtle sulfur isotope shift in the dissolved sulfide in the Black Sea water column associated with oxidation, and maybe rates of sulfate reduction. You can actually see that the pyrite gets in the traps as well, but from the isotopes, not only that it's forming in the water column, but where in the water column. So if it went through a precursor phase, which almost certainly it did, it was really fast, right? And it's depositing as pyrite, and those sediments have no ABS or no monosulfide. The place where I showed the very rapid sedimentation that was in euxinic environments, it's on the upper slope of the Black Sea. So it has the capacity to do the scavenging, but there's such an incredibly high detrital flux that it swamps that scavenge component, and the iron as well as the trace elements look continental. So that's getting to Nick's point. That's a place that you would say is oxic, even though it wasn't. That has a ton of iron monosulfide. There's a ton, like black, 0.7, 0.8 weight percent of of ABS sulfur in those. And you actually, in many cases, can see a crossover where the ABS is dropping as the pyrite is increasing. And there's this fundamental question about the pathway of how that's happening. The traditional view is as well as I do, is using sulfur intermediates. But in that case, we argued in a paper that it might be H2S that's doing it because they're probably unheated.
This question, what is the texture, the sizes, and the forms of the
So the pyrite in the Black Sea, again, the Black Sea taken to the nth degree as our model for all things. They're very small framboids. They're about 10 microns, and they're very uniform in size. And Rick Wilkin and colleagues at Penn State developed a framboid-sized proxy for Euxinia. And the basic argument is that things that form in the water column form to a certain size, and then because of Stokes law, they settle out. And then they get to the sediment, like in the Black Sea, where there's no more reactive iron, and so they don't grow any larger. And so small and uniform framboids, and there are exceptions to this, but that's the side of Euxinia. Whereas diagenetic pyrite that's forming in the sediment and supported by the sediment can become big. So the framboids tend to be bigger and more varied in size.
Yes or no? Any marker study?
No, we don't really look for that, but it's there's no indication of that. Probably because the pH isn't right for it to be, my guess. I don't know of any others. In the Black Sea. Oh yeah. Yeah, no, I know. Yeah. We'll talk. Yeah.
Anyway, thank you for coming again.